presentation is the name of the research project carried out by the University of Madrid. It's called Ion Beam Shepherd for Contactless Space Debris Removal. It's an exploration of a new technology which gave us very interesting results, unexpected results, and maybe it can be even called a new line of research, since nothing like that has ever been done before. We had a lot of fun working on this in this project. I would like to thank the collaborators, which are the two students, Mario Merino and Odayo Luchua from UBM, Technical University of Madrid, the two professors, Eduardo Edon and Jesus Pelay. Then I would like also to say that the ACT was involved in different steps of the project in different aspects, and I'd like to mention Joris Olimpio, Dejan Petkov, and Leopold Sammer for their contribution. Quickly, what is this all about? The ion beam shepherd, it's the concept of using an ion beam in a different way as it is used normally. Ion beams are emitted by electric propulsion system all the time in current space application. Here the idea is to use the ions of an ion beam, their momentum, to move objects in space in a controlled manner. In this picture here, you can see a basic scheme of the concept. You have a Shepard spacecraft with two engines. The main ion engines is the one that shoots up ions and directed towards debris, here particularly an upper stage, and moves it. For example, you can think about a slow deorbiting maneuver of the debris. At the same time, clearly, in order to keep a constant distance between the two objects, the two spacecraft, a second propulsion system is needed to cancel out the relative dynamics between the two spacecraft in orbit. The evident advantage, primary advantage, is that it's a contactless method. It doesn't need to have any docking maneuver between the shepherd and the debris, and is ideal for debris whose dynamical state can be tumbling or spinning uncontrolled. They may be unknown and are completely not cooperative. It relies clearly on low divergence ion thrusters, but they do exist in reality, although they can be improved, and such an improvement, for example, in terms of divergence, may certainly benefit the concept. The original idea started being proposed by Technical University of Madrid in 2009. We went also through a patent application. Interestingly, independently, both JAX and CNES hit the same idea, and pretty much around March, April of 2010, the three of us started presenting the idea. And I think that this is a positive thing. It means that somehow there is a common way of thinking when a common problem shows up. I would like to add also the fact that the concept can also be used for asteroid deflection. It's a different type of problem, but have many similar aspects, and we presented some recent work at a recent planetary defense conference in Romania about that. What is the study about? What we did look at? Well, the whole concept is completely new, so we had to try to quickly identify the key aspects of the problem. First of all, we wanted to see if the concept works from a preliminary level. I call it a system study. Maybe it should be better defined as a performance study. We did basic design optimization of the thrusters. We computed the orbit performance for large debris. That's the target we are currently looking at. We are using this concept for dealing with large objects. That does not mean that small objects should not be dealt with, but for our concept, this is the target. Clearly, we wanted to know everything about the way an ion beam expands, the momentum it carries, and how it interacts with an object. So we needed some models which could be accurate enough, but at the same time fast enough in order to then insert this beam dynamics model into a more general orbital dynamic software or model. So we did quite a lot of work on this ion beam modeling, and we found some very important results in the literature, which we tested extensively. Later on, we took this model and we started integrating it into a simple dynamic model in which we computed the transmitted forces and torques to a solid body of generic shape. We realized that we also had to compute gradients of these forces and torques in order to then get good information for equilibrium. We found interesting non-trivial equilibrium configuration, which I will show you in the long presentation, not in a half. Then we moved to orbit. We set up a relative motion, orbital motion dynamical system, basically a proximity formation flying model. And we studied the stability of the relative position. You can think about two objects co-orbiting, one at close proximity, think about 10-15 meters, but there is an ion beam in the middle. So the thing is to find out, to understand what does the ion beam do to the stability of this dynamical problem, if it is beneficial, if it is not, and what kind of control strategy can be implemented. We also briefly looked at the use of tethers as an alternative to using a secondary propulsion system. At the beginning, we thought they were very promising, but then we found some stability problems. In any case, we will not discuss this in this presentation. You will find them in the final report. Just to give you the main results of the studies, from a performance point of view, you can have, just to have a number in the head, in mind, an IBS of less than 500 kilograms after a preliminary optimization can deorbit up to 10-ton debris mass from 1,000 to 300 kilometers altitude in less than a year, which means that the concept is feasible for large-sized debris. Clearly, another important output from the study is that high specific impulse is paramount. Why? Because the mission time it's long, and then the Stullinger characteristic velocity is high. That means the optimized specific impulse in order to minimize the propulsion system mass, power and propulsion system mass, is high. So if any of you work on a high specific impulse propulsion system, you found a very interesting application for your work. How about the plasma beam modeling? We checked what we could do with commercial thrusters, because that's what we always think of when we start working on the demonstration missions. And clearly ion engines are the current best candidates because of mainly their divergence, low divergence. In particular, there are specific types of ion thrusters which has very low divergence, like 4 grids one, and these are quite interesting. We selected 3 far-field plume self-cylinder models for the expansion of the plume and compare them and decide what the differences are between them and what would best fit our needs and expectations. We analyze them in great details to understand the main physics of the problem. Then we also looked at the influence of environmental effects on the beam dynamics. We could see that ambient plasma, even in LEO, it's negligible. And geomagnetic effects, which tend to bend the beam, seem to be negligible for the control distances that we are looking at first sight. On the other hand, due to the very high complexity of the model, we would need confirmation of that, resorting to more complex tools or models, which go clearly beyond the scope of this preliminary study. We explored the ion beam interaction with a solid body. We soon realized that we had to introduce key non-dimensional parameters for such a humongous parameter space, and it proved very effective to introduce them to summarize the main aspects of the interaction. We calculated action and radial transmitted forces, torques, momentum transfer efficiency, gradients, and mapped across this parameter space. Interestingly, we found some non-trivial equilibrium solution for a cylinder. I see Christophe Bonal looking at me as if they found the same. It would be interesting to discuss about that. As for the relative motion dynamics and control, we found, and that could also come from the intuition, that the beam perturbation is stabilizing in the along track, but destabilizing in the already unstable radial direction, the R bar. So the open loop problem, relative dynamics problem with an ion beam is not stable. And the ion beam does not stabilize the system. That would be great. It doesn't happen. On the other hand, a three-axis proportional and differential feedback, derivative feedback feed-forward control system was developed, and we could test its capability in stabilizing this co-orbiting configuration. The attitude stabilization, and here I'm referring mostly to cylindrical bodies, is more challenging, but there are potential equilibrium, stable equilibrium configurations that would need a little bit more work in order to control against external perturbation. I will show you more about that. And I think that the best summary of that is a simulation that we carried out. You see in this movie a cylindrical body under the effect of an ion beam. This results comes out of a software that we implemented during the course of the study. And you can see that given the complex dynamics, we have here only a position control, not an attitude control. You will see that in orbit the beam does make the attitude wander about in this kind of seemingly chaotic manner. And certainly there is a lot of work to understand what's going on here. But I will certainly give you more details in the study presentation if you stay around, or otherwise check the final report. And I think that is all for this introduction.
Okay.